So our first example, we have y equals x cubed minus 6x squared plus 9x plus 2. So the first step was the domain. I don't have any square roots here. I don't have any fractions. It's not a rational expression. I can evaluate it for any x I want. So my domain is all real numbers. X and y intercepts. So the y-intercept, again, is pretty simple. Plug in 0 for x, and we get the y-intercept. So my y-intercept is just the ordered paired 0, 2. X-intercept, we don't really solve cubics. They're not very simple to solve, and this one in particular is not even factorable, I don't believe. So I don't want to try and solve that. I'm going to have enough information to still have a good sketch for it, but I'm not going to bother trying to solve it. Again, if I had a graphing utility, a graphing calculator or something to solve it for me, that would be a different story. So we're going to go to number 3, and that's going to be vertical and horizontal asymptotes. Well, I don't have a rational expression, so I'm not going to have any vertical asymptotes, and I don't have any horizontal asymptotes, so I'm done with that. That's just a none. Number 4, intervals increasing, decreasing. And then number 5 is extrema. So I can kind of put these two together. What I'm going to do is I'm going to use the second derivative test for this. So y prime is 3x squared minus 12x plus 9. Y double prime is 6x minus 12. So if I set this equal to 0, I'm going to factor it. So first I'm going to just pull out the greatest common factor of 3, and then factor it further, and it factors to x minus 1, x minus 3. So x equals 1 and x equals 3 are my critical numbers. I'm going to go back over here and evaluate them in the second derivative. So when I plug in 1, I get negative 6, which means this thing is concave down. So I have a realm max at x equals 1. And I want to know the ordered pair, so I'll figure that out in a second. When I plug in 3, I get 18 minus 12 is 6. It's positive, which means it's concave up. So here I have a relative minimum at x is equal to 3. So I want to know the y values that go along with it. So in the original equation, back up here, when you plug in 1 into this equation, then we get a point of 1, 6. And I just plugged this in my calculator before. And then when I plug in 3 back into this original equation, we get a y value of 2. Alright, so I'm done with the relative extrema. I didn't specifically write it, but if it's increasing and then decreasing, right, that's when you get a realm max. So the intervals that it's increasing is going to go from negative infinity up until 1. And then, again, it was decreasing. Then it's increasing again after it hits 3, right? Because this interval was a low point. Now it's going back up again. So that would be from 3 to infinity. And then it's decreasing on the interval from 1 to 3. Now, you don't have to use the second derivative test to do this. You can do the number line. In our next example, I'm going to do it out the other way, all of it on the number line, just so that you can see it both ways. Okay, so now we need to find out, where are we? We're determining concavity. So I already found the second derivative, and it was 6x minus 12. Set that equal to 0, and I get x is equal to 2. So if I pick values, again, this is my second derivative. So if I pick values like 0 on one side and 3 on the other, When I plug in 0, I get a negative value. When I plug in 3 into this, I get a positive value. So it was concave down on this interval, and it's concave up on this interval. 2 is in my domain, so it is a point of inflection. So my point of inflection is 2. And again, to figure out the y coordinate that goes along with it, you have to go back to the original equation and plug in 2. So when you do that, it gives you a y value of 4. So I'm going to put all this stuff together. The y-intercept was 2. It had a max at 1,6. It has a minimum at 3,2. It has a point of inflection at 2,4. So it was increasing until it hit that point there, that max at 1,6. And then it was decreasing. And remember, it was concave down on that interval until it hits this point, 2,4, that point of inflection, and then it changes concavity. It hits its minimum value at 3, and then it's increasing again. So that's what the sketch of the graph looks like. Now, I did it on a computer-generated application for your notes, so it looks a whole lot nicer than mine, but you can see it's the same sheet. All right, and then we have f of x equals x plus 1 over x minus 1. All right, so first part, domain. Well, it can't be reduced away, and if I had 1 down here, it would have division by 0. So it can be any real number except for 1. The y-intercept and the x-intercept. So the y-intercept is when you plug in 0 for x. So when I plug in 0 for x for these, I get 1 over negative 1. So I get a y-intercept of 0, negative 1. The x-intercept is when you plug in 0 for y. So if I plug in 0 for y, that means the numerator has to equal y. So I get negative 1, 0. We have a vertical asymptote at that x equals 1. And horizontal asymptote. So the degrees are exactly the same. We take the coefficient of those degrees. So horizontal asymptote is y equals 1, because I just get 1 over 1 for that. Four, we're going to look at the intervals where it's increasing and decreasing. So I need f prime of x. And when I took that derivative, I got negative 2 over x minus 1 squared. So the only value, critical value here is 1. Because that's what makes this division by 0. That's where it's undefined at. So I'm going to plug in 0 and 2. Well, because I'm taking a number down here and I'm squaring it, it's always going to be positive. 2 is never going to change, so it's always just going to be a negative. So I'm negative on either side, which means it's decreasing to the left of 0 and it's decreasing again to the right of 0. I'm sorry, 1, not 0. And I have to break it up because the function doesn't exist at 1, so I can't write it as one big interval from negative infinity to infinity, because that wouldn't be correct. There is no relative extrema because we said it doesn't exist there. And now I need to know the second derivative. So the second derivative is 4 over x minus 1 cubed. Again, 1 is the only thing that I have to worry about. That makes it undefined. So I'm going to put in 0 and 2. This time, this cube here is going to keep the sign. So if I plug in 0, I get a negative, which tells me it's concave down. If I plug in 2, I get a positive, which tells me it's concave up. Again, there's no inflection point because the function doesn't exist at 1. So I have a y-intercept at -1, an x-intercept at -1. I have a vertical asymptote at +1, and the function is leveling off to 1 because of the horizontal asymptote. So that means it's going to come down, cross there, and then it's decreasing the whole time. And then on the other side of the asymptote, it's decreasing. So that is what our function looks like.